The broadcast is now starting. All attendees are in listen-only mode.
Mic check 1 2 3. Okay. Okay, good morning. We're gonna wait just a couple more minutes uh, for everyone to arrive. Before we get started, if you could please click on the raised hand button along your webinar or toolbar, so I know that you can hear me. Okay, great. Okay, we'll wait another minute or two, and then we'll get started. If anyone's having any trouble hearing me or seeing my screen, right now you should be seeing a PowerPoint presentation. If you could please just send me a question. Okay, so it looks like everyone is here, so we will now get started. My name is Ted Blow. This month we will be talking about modeling basic heat transfer processes using GoldSim. Okay, and the agenda for this webinar is: first, I will give you an introduction about myself because this is the first time I'm presenting. We will give an overview of the general GoldSim model that is presented, key assumptions associated with that model, a schematic of what it looks like, the methodology we use to model heat transfer, the energy balance, and then we'll kind of go on a tangent on the energy balance to discuss a simpler model so that we can first understand the concepts and then apply it to our application model. We will discuss how the thermostat is controlled and go into the results and limitations. And I would like to add that there was a question on how the solar radiation was modeled at the last presentation, so I added a couple slides at the end. Okay, so again, my name is Ted. In my free time, I like to spend time with friends and family, doing social activities and hiking and being outdoors. Professionally, I've been with GoldSim since 2020, so about a year and a half. And before that, I was a mechanical engineer for Orano Federal Services in the nuclear packaging division. And then before that, I was at school getting my master's and bachelor's in mechanical engineering at Texas A&M and Gonzaga. So our model today, we are going to model a couple of heat transfer modes and interactions between the environment and a one-room residential building. We're going to look, and with those interactions, we hope to calculate the heating bill associated with maintaining a comfort level inside that room. We are going to model the solar radiation from the sun, the convection from the outside ambient environment to the outside surface of the wall and roof. We're going to model the conduction through the construction layers of the walls. And then inside is going to be a small electric heater to maintain a comfortable temperature for the occupant. The thermostat is modeled in two scenarios. Maybe I shouldn't say the thermostat. Our model is consider two scenarios. One, which is pre-COVID, which is where we commute to work, so we're not at home, and we set the thermostat to a lower temperature throughout the day to conserve energy. And the second scenario is COVID, where we work from home, and that is where we maintain our set temperature throughout the day. So that is an overview of what we're going to be modeling for the big model, and a couple of key input parameters and assumptions. The simulation goes for 1 month at 1 minute time steps through the month of January. Throughout the month, we are considering only clear sky conditions, so there's no clouds. And this clear sky solar radiation methodology is used to calculate the heat load for heating, ventilation, and air conditioning and solar applications. We are going to use a basic thermal network that is like an equivalent electric circuit, composing of 3 resistors and 2 capacitors for our construction layer. So we'll get into that a little later. But it basically means that we're calculating temperature as only a function of time and not of spatial orientation. The ambient temperature varies every 5 minutes, and the solar radiation varies hourly. And we will combine these into an effective temperature. The walls are vertical, the roof is horizontal, both of which are constructed of multiple layers. We are not considering heat transfer through the floor, and constants are used for the outside and inside wall surface heat transfer coefficient, meaning there's no variable wind. Our internal zone is empty, meaning that there's no chairs or lights or people or anything like that that would give a thermal resistance. And then the heater in this model is used as an electric baseboard heater, which means it's either a constant power output or it's off. Okay, so here's a schematic of the model. We have a rectangular structure that has vertical walls, horizontal roof. There are 4 vertical walls in this orientation. The thermostat controls the temperature, the outside environment we have a data set for, as well as like the radiation data. Again, we're not modeling the floor, we have a heater. So this is the basic schematic of what we're modeling. Okay, so I alluded to this before. Actually, you know what we could do? Before we get into this, I'm gonna show you some results just to get an idea of what we're gonna be looking at. So here's our result dashboard. If I run the simulation for both of our scenarios, okay, so we can see in our plots that we have the outside temperature. And if we pop this out, we can see that the outside temperature, this is like the outside surface temperature. And this is, the blue one is of the north wall, the green is the ambient, the gray is the roof, and the red is the south wall. And this has to do with the orientation with respect to the sun. And we know that the north wall is going to be a lower temperature because it's in the shade, as opposed to the south wall, which has the most exposure to the sun throughout the day. So that's an overview of the outside temperature. Our set temperature varies throughout the day, depending on our comfort level and depending on if we're home or not throughout the day. The heat flow throughout the house, this is the heat leaving the house throughout the day. We'll go into these results at the end, but this is kind of an overview of what the results look like. Okay, so before we get too much into the results, we're going to go back. Okay, so we're calculating these results based off of what is termed a thermal equivalent thermal network, or a low order thermal network, or a lumped capacitance model. And what that means is that we can represent each zone using resistance and capacitances, and that has an associated low computational cost. This is the simplest way to model transient conduction, and not only transient conduction, but transient heat transfer. And so each node or body, being a wall or the internal zone or the outside or the roof, only changes with respect to time. There's no spatial variation, which means we don't have to discretize each component. The entire body changes at once throughout. Okay, so what does this mean? The body changes throughout all at once. Well, if we look at this simple example, we can see that this orange body represents a small sphere or just a small body. This is immersed in a liquid indicated by the blue. It has an initial condition, and the solid has various properties like a density, thermal capacity, and volume. The outside environment has a temperature and heat transfer coefficient. So if we take an energy balance of this system of our body, then we can say that the energy coming into the body minus the energy leaving the body plus the energy generated within the body is equal to the change in energy within the body. So in this example, the body has an initial energy, an initial temperature, and energy is leaving the body via convection to the outside environment. So if we simplify our energy balance, we can say that there's no energy coming in, no energy generated within. So we say that the energy leaving the system via convection is equal to the change in energy within the body. So the convection is equal to the convective heat transfer coefficient times surface area times the difference in temperature of the body to the environment. And the energy is just basically the thermal mass associated with the body. So how do we relate this to a network? What is the resistance and what is the capacitance? So if we build our network, we can say that each node represents temperature. And we say that the environment is an infinite sink, meaning that its temperature is constant throughout the course of the simulation or is independent of our body. We can say that this temperature, T infinity, is this node. The temperature of our body is T, this node. And this body, the small body, has an associated mass with it or an associated energy. So we model that as a capacitor, where the capacitance is the mass times the specific heat. And it changes with respect to time. And temperature is just a measure of that energy. So if we, and the resistance being the heat transfer coefficient over the surface area is the resistance. So if we take our energy balance and convert it to this circuit, we can say that the energy, this is negative because energy is leaving the body. So if we say that the temperature of the body to the environment over the resistance is the rate in which energy is leaving the system is equal to the thermal mass of the body over time. So this is how we model it using an effective thermal network. Okay, so now we're going to look at this model in GoldSim. So what does this mean with respect to, actually, no, I'm gonna go one more. Okay, so now that we understand the concepts of the energy balance of a body changing with respect to time. And now that we understand the thermal equivalent network, we're now going to talk about how this relates to GoldSim and how we model this using GoldSim. And the element that we're going to use is a stock element, particularly the integrator element. And we're using the integrator element because the rate of change can either be negative or positive, and it can change throughout the course of the simulation, and it'll be okay. You can model this using using a reservoir pool, but you would need to include if logic in your model to account for the sign change. Okay, so our internal energy, so the stock element is basically defined by a value which is equivalent to the initial value plus the rate of change. The value that we're interested in today is energy. The initial value is the initial energy indicated given by the initial temperature, and the rate of change is the mode of heat transfer outside of the body. And the model that in the simple model, it was convective heat transfer. So we put our convective heat transfer in the rate of change. Our initial energy depends on the initial temperature. And then we multiply it by the thermal mass capacity, the mass times the specific heat, and we have our initial energy. Okay, so let's look at a basic GoldSim model of this so that we can combine everything that we've just learned. Okay, so here's our GoldSim model. This is our small sphere. This has our internal energy node and our temperature. The stock element represents the capacitance. The temperature is just the measure of energy. The energy leaving the system is the convective heat transfer away, and then our environmental temperature is constant throughout. So if we run the simulation and the initial temperature of the sphere is higher than the surrounding environment, so energy is going to be leaving. And we can see our results that the energy leaving dissipates throughout the course of the simulation, and it eventually reaches the temperature of the environment over a period of time. Okay. So now that we have seen how to do the energy balance, how we've seen how to model this in GoldSim, create a thermal network, and apply to a simple example, how do we model a building doing this? And the first thing we do is we perform our energy balance on our system. What are the different interactions in our system? First, we have the solar radiation from the sun, and we know that this changes throughout the course of the day depending on the time and our specific location. So, this is I have time series data from a data set, and we're gonna, in terms of like energy, so we have, or I think it's the flux. So this is going to be combined with our ambient temperature, which is also a data set in a time series. And we are going to combine these into an effective solar air temperature. And this calculation method is common for heating and cooling load for building applications. And this is going to give us like an effective temperature that incorporates like the input energy from the sun. And we are going to say that there's going to be convective heat transfer on the exterior surface of the wall interacting with the environment. The thermal mass of the wall is broken into two. Half of it's on the outside and half of it is on the inside, which is why we see half of the thermal mass of the wall on this node and then half here, because this is on the outside surface and this is on the inside surface. And we have conduction between the layers. This wall has multiple layers and we combine it into one. We combine it in series into one resistance. There is convective heat transfer from the inside surface of the wall to the zone. Our zone has a thermal mass associated with it, and that is the inside thermal mass. And then the heater is just a direct heat input into the wall. So this thermal equivalent network is a little more complicated than the one that was showed before, but the principles are the same. And this goes into a little more detail of what we just saw. And this is how we're going to model the energy balance in the actual GoldSim model. So again, we have our solar air temperature, the resistance to convection, resistance to conduction, resistance to convection on the inside. And here is our capacitors, which is half of the wall on the outside surface, half of the wall on the inside surface, and then the air in our zone. And then the heater coming in, the heater heat coming in. So we perform 3 energy balances because we have 3 nodes that we want to calculate for. And I'll show this to you in the GoldSim model when we go there. Actually, I could just show you right now because we're talking about it. Okay. So that is that one, and then this one. Okay. We will reset the model. And we will look at our internal walls. So this is the energy balance that we just saw. This is for the outside surface. So the outside surface has an integrator element because it has a mass associated with it, a thermal mass associated with it. And we see that, and all of these are highlighted in orange because they are vectorized, because we have 4 walls. We have the north, south, east, and west. And I created an array label set for that, indicating the orientation of each wall. And I highlighted it in orange so I know what's a vector and what's not a vector. So we have the initial energy of the wall, which is indicated by an initial temperature times its thermal properties and geometry. And so that's the initial energy. And then the heat leaving this wall is the energy going to the outside and the energy going to the inside surface. The outside is the convection and the inside is conduction. And then this is the inside surface, and the energy interaction with the inside surface is the energy going to the outside wall and the energy going to the internal zone. So we see our resistance, we just perform our energy balance at each node. And this has the walls. The roof we'll get into a second. So the inside zone has the same thing. We have the energy leaving to the walls, the energy going to the roof, and the energy from the power, from the heater. Okay. And then, okay, let me switch back to my presentation to show. Okay, so now that we have seen that for the walls in the internal zone, we just apply the same methodology to the roof. This is a flat roof. It has the same T-solar air. The T-solar air here is slightly different because this is a horizontal orientation and this is a vertical orientation. So the details are slightly different, but the method is still the same. So we have the resistance to convection, the outside surface, conduction, the inside surface, and then convection to the inside air zone. So let me show you the roof in the model. So the roof, it's the same method as the external walls, the same energy balance. And let me show you these walls. So this is representative of each layer of the wall. Each layer is made of a different construction material. And then the resistance of each layer is added in series. So it's just added together into an effective R2 resistance. And then the specific heat for each layer is also added into the wall specific heat. And the same method is used for the roof, where we combine the resistance into an effective resistance and the capacitance into one effective capacitance of the roof. Okay, so now we understand how to apply this equivalent thermal network to our building application. Okay, so now that we understand now that we understand the energy balance for our system, we can look at how are we going to control the temperature within the building. And we're going to do that using a couple different features. The first feature that we're going to use is we have to set our set temperature throughout the day. Now, the plot earlier, we showed that it varied throughout the day, and it depended on each scenario. And this changes, from person to person depending on your personal comfort. And so now let me switch to the GoldSim model Okay, so let me switch to the GoldSim model and show you how we model this thermostat. So we start with the set temperature. This varies hourly throughout the day, and it depends on our scenario. So one is our scenario where we are working from work, where we set the temperature low throughout the course of the day, and then this set temperature is COVID, so we are here all day. So we set the temperature higher. So we set our set temperature, and associated with this set temperature is a dead band, because we don't want the heater to be oscillating. And in this case, like this thermostat, what is a dead band? It basically means we set the temperature at 70 degrees, and then the heater turns off at 71 and it turns on at 69, because we have the upper and lower bound. This feeds into the status element, where we say, if it's less than this, turn on. If it's greater, then turn off. So our deadband, our set temperature, and our deadband feed into the status element to tell the heater to turn on or off. And then this heater feeds into the heating cost, which we have the price of electricity, which varies hourly throughout the day because the price changes over the course of the day depending on demand. And we multiply our power times the cost, and put this in an integrator element to give us the cumulative cost so that we have our final heating bill at the end of the month. Okay, and then again, the heater size is just a constant that we can modify in one of our dashboards as 8,000 BTU per hour. Okay, so now that we know, and actually I can show you the control dashboard. So if we want to change our settings and inputs here, we can vary that in our dashboard and change our heater size. So if we go back to the results, run our simulation again, so the outside temperature, again, it varies. At night, it goes to the same temperature. You can see that like there is a small variation, and the reason for the variation is the convective heat transfer on the external surfaces. We said that it's constant, and so that's why there's a small delta between the ambient, the green temperature, and our other temperatures. So at night, it goes to relatively the same temperature, and then throughout the course of the day, it changes based off of its sun exposure. And then our set temperature, again, at night, it's the same for the two scenarios. And then when we wake up at 8 o'clock in the morning, we either go to work at home and the temperature is set so that we can maintain maximum comfort, or we set it low so we don't use unneeded energy. And then when we get home, we turn it back on from when we get back to work, or it just stays on as normal because we're already at home. And then when we go to bed, we set it a little lower. Okay, and then, yeah, let's go to the inside temperature. So this is just a 1 day within the month. And we can see that the inside temperature coincides with our settings. So again, when we wake up at 8 o'clock in the morning and leave for work, we turn the temperature down and the inside temperature goes down and then oscillates between our dead band. And then the same is true with the inside. It takes a little longer to get to temperature, but once it gets to our set point, it oscillates between the dead band. And then what does this mean for the heat flow throughout the construction? When we are home, there's going to be more heat leaving the house because we're at home and we have the heater on. And we can see that even though we have the same set temperature at night, the heating is different because the heat doesn't recover from on a diurnal process. This is, again, this simulation is run for an entire month and the temperature oscillates. So it's not diurnal in the way from scenario to scenario. But we can see that, when we go to work, the energy drops because the temperature drops, so the energy leaving is lower because there's a smaller gradient between the inside zone temperature and the outside temperature. Okay, so that's the heat flow out of the house, and then we can go to our monthly heating bill, and we can see that before COVID, our bill was $45, and during COVID, it's $66, which makes sense because we're at home where the set temperature is higher and we use more power. Okay, so I still have some time, and I want to discuss the solar radiation because there's a question from the last presentation. And how exactly do I calculate the solar radiation and what goes into that? So the radiation we can think of in terms of the shortwave radiation, which comes directly from the sun, which has a wavelength of 0.3 to 3 micrometers, and has two components. It basically has the beam component and the diffuse component. The beam component comes directly from the sun, and the diffuse component comes from uh, like various angles when the beam diffuses in the atmosphere, and it hits the surface from different directions. And then we have long wave radiation, which has a wavelength of 3 micrometers or longer. And this basically is interaction between different objects. And this is conceptually, long wave radiation is the reason why you can still see things in the shade, because sunlight bounces off and then it interacts with different bodies. And if long wave radiation didn't exist, then it would be pitch black and you can see in the shade. And we are not considering this because it is difficult to calculate. And there are some estimations that you can use, like for example, this is 0 for vertical walls, but it's hard to calculate, and I did not include it in this model. So only shortwave radiation is considered. And that is basically the surface's ability. So it's a surface material property, the absorbance of surface, the absorptance of the surface, and multiplied by the total solar radiation incident on the surface. And this is composed of both the beam and the diffuse. Okay, and the beam originates from the solar disk, and the diffuse energy originates from the sky dome. And the angle is the angle of incident on the receiving surface. And if we look at this figure on the right, we can see that the surface, it depends on whether it's a vertical orientation or on the horizontal orientation. But the way we calculate it is we start with the horizontal surface, and then after we calculate the two components for that, for the horizontal surface, we can then transpose it to a tilted or vertical surface. So the global total irradiance, which is indicated by this equation, is equal to the direct normal irradiance times the cosine of theta, which is the angle of incident on the receiving surface, plus the direct horizontal irradiance. And the DNI, this is the beam component, and the DHI is the diffuse component. And so the DNI and the DHI are given in the data set, and then from that we calculate theta separately in separate calculations, and then we can calculate the GHI, and then we transpose that for our vertical surfaces. And that is how we calculate the solar radiation on the surface, and then we convert that, and then we add that to the ambient temperature to get the solar temperature. And so that is some discussion on the solar radiation and some basic limitations. So the first limitation, as I stated, is inherent to the transient methodology we use, which is the thermal equivalent network. And this network says that each node that we calculate only changes with respect to time, and there's no spatial variation within each node. So that's an inherent limitation. We assume that the inside zone is empty with no loading, no lights, no people, no desk or furniture. I use constants for the heat transfer coefficients. on the outside and inside surfaces. I do not consider the floor in the house. The roof is horizontal. You could make it a pitched and include an internal zone to represent the attic. I do not include any windows or any air leakage into or out of the system. Looks like we have a question. Could you include an optimization to define the optimum lower temperature bound with the house while the house is empty? Yeah, that's an interesting idea. It would be interesting to see if you can include an optimization to define the optimum lower temperature bound. Yeah, that would be interesting. Because if we look at our results, oops. So the inside temperature we can see in this plot on the bottom right-hand plot that with this set temperature at 60 degrees, it never recovers. So at midnight, it's 65. Maybe we're freezing at 65. So maybe you could do an optimization. That would be interesting to investigate. But certainly, like there is an opportunity to optimize this value because like you never recover and you may be cold. So that would be interesting to look at. Okay. Um, Okay, so future applications, I think it would be cool to, instead of looking at an electric heater, you could model a furnace um, and air conditioning if you wanted to model for the cooling load in the summer months. And you could, by doing that, you could include more input parameters and uh, calculate it using different sources, so different methods. So that would be really interesting to look at. You could look at multiple rooms with instead of having one room to represent a more like either a bigger house or a different situation. And then what I think would be fun is if you made your house and then you cloned your house to make a residential city block or city to project the heating demand throughout the course of the year, heating and cooling electricity if you're a utility. So I think that would be cool too. And that is all I have for today. So if you have any questions, I will stay on and answer any questions. And I thank you for your time and look forward to talking to you next time. So thank you. Okay, it looks like we don't have any questions. So I will now end the webinar. And again, thank you for participating today.